So this is the third YouTube video to show the importance of electro-diffusion for the analysis of voltage in dendritic spine. So in this video, I will present a method for estimating the effective resistance of the dendritic spine neck. So most of the software are available on our website www.bionewmetrics.org. And so this YouTube video is part of a comment that present and provide more explanation for our Neuron paper published in 2018. So the main question we are going to be interested here in is how to extract the spine neck resistance using electro-diffusion model, PNP, Poisson-Nernst-Planck, from the transient dye responses monitored in the head and the base of a dendritic spine. So specifically, let me show you the frame for this. So we have here a dendritic spine. You can see here two regions of interest, R1 and R2. A stimulation, a synaptic glutamate engaging occur at this red spot here. And so we are interested in the analysis of the transient response in these two regions. So this is the schematic representation. We have the fluorescence that should be proportional to the voltage here in the head. We have some information that could be extracted, which is the length here of the dendritic spine, but the radius is too short to be extracted. So this will be a parameter that will be explored later on. And finally, we have the information about the fluorescence, the voltage that can be described from the fluorescence inside the dendrite in region R2. And so in parallel with the measurement, we can perform numerical simulation to calculate the voltage in the head once we know the voltage at each point. So here the voltage in the head, in this case, will be given. And we can always assume that the voltage in the dendrite is 0 because the voltage is defined up to a constant, so we can subtract a constant even if the constant depends on t. And this is unimportant in the Poisson-Nernst-Planck equation because it disappears. So the relationship between the measurement and the simulation will be that the voltage in the head will be the difference of the voltage estimated from the fluorescent in the dendrite minus the voltage here, there's a mistake, voltage recorded in the head. Oh, I'm sorry, V head minus V dendrite. So the Poisson-Nernst-Planck equation for the voltage. So here we are going to make the following model and approximation. Instead of considering the entire Poisson-Nernst-Planck in the entire structure, we are going to simulate only in the neck. Why is that? Because the fluorescence will give us the information inside the head. This is in region 1, while we'll get the information about the voltage from region 2. So the only missing part which we are interested in is to estimate what happened inside the neck and especially to estimate the resistance. That's why we are going to only use a model, a 1D model, approximated model for Poisson-Nernst-Planck inside the head, inside the neck. So those are the equations. So those are the classical Poisson-Nernst-Planck equation. The first one is for the voltage. This is the Poisson equation for positive and negative charges. We have then the Nernst-Planck equation for the concentration of positive charge and for negative charges. And V here, the voltage, represents the difference of voltage between region 1 and region 2. So then we need not to discuss the boundary condition. The initial condition here are not important because we are studying a transient problem. So this is now, let me remind you, the classical boundary conditions. So we have here the condition at the position L, which is here. So this is the connection with the dendrite, which imposes here a given concentration for the positive and negative species. We have then the condition for the fluxes at the entrance, that is here. So we inject a current, the current is injected. So this is important here to notice that the current here is not the synaptic current. It is the current that is flowing from the head here to the neck, which can be different from the current, from the synaptic current. And finally, we impose this boundary condition for the voltage at the entrance, dVdx equals 0, and no fluxes of negative charges. So yeah, this is something I would like to insist on, is that the synaptic current, the current that is entering here, is not necessarily equal to the current that is flowing inside the neck. However, this is not going to be that important because we are going to have, as a piece of information, the voltage changes reported here by the voltage dies. So the synaptic current, I stimulation, and IT are not necessarily the same. I mean, there are many reasons for this, because the current ions can flow and can be extruded on pumps located on the surface of the spine head. Okay, so now we are going to make the following assumption. We are interested in the current that is flowing from the head to the neck. We'll call it I of t. And we'll make the assumption, using this following expansion, that it is proportional, this current is proportional to the voltage in the head, to its derivative, the third derivative, and so on. Where we assume that in this expansion, we have a dominance of the first term with respect to the second with respect to the third, and so on. So here we are going to make a truncation. We are going to neglect this all of the series, and we are going to truncate here to order 2, so that I of t is going to be proportional to a constant which we call g of t multiplied by v head plus c dv dt. And so what we'll be interested in here is to calculate this g and c, because v of t here, v of t and dv dt, we have it from the information from R01, from this region of interest 1, right? So v and dv dt we have, but g and c are unknown. And now we are going to estimate these two quantities. So here is the general pipeline of our methods. We propose to use simulation of P and P for the voltage to compute this C and G parameter. So we have no idea in principle of what is C and G. So those are the unknown, and we fix some spine parameters such as the concentration at the dendrite. We are going to fix also the spine neck radius, although in the supplementary information of our Neuron paper, we show what is the consequence of looking at different radius. So we fix here the radius, for example, at 100 nanometers. Then we use P and P to calculate the voltage numerically, and this will allow us to estimate the voltage in the head. So for a given couple of parameters C and G, we can simulate or we can estimate the voltage here in the head. So now how are we going to do this? So let me now explain this. So we have, as a function of time, we know the voltage. Here this is the difference of voltage. It's V1 minus V2 as a function of time. So the blue curve is the measurement, and the yellow one is the one calculated from PNP for a given C and G. And so what we are going to use as another piece of information is a derivative, the slope here, as you can see, the derivative of the voltage as a function of time. And we are going to select this pair GK and CK, so I'll explain in a minute how we do this exploration of parameter, such that these two slopes will coincide. That is, if you look here, what happened, we have one slope obtained by the measurement, the other one obtained by simulation. And if we do a good job in the estimation, we are going to end up to something that where the two slopes do coincide. So this is an example of the iteration to calculate C and G. We start with a case where they do not necessarily coincide here. And as we move on in the process of iteration, which I will explain in the next slide, we are going to have a good matching here. And if we have a good matching here, and if the theory is correct, what we said is we should have a good matching in the entire 0 to 400 milliseconds, right? If the theory is correct in the transient process, then if we have a good matching here, we should have a good matching everywhere. And this is really the key point of the methods we have developed. That is, if the theory is correct, we should be able to predict over a sufficiently long period of time. And why we stopped here at 400 milliseconds, because we observed that there were then fluctuations in the data. And these fluctuations are not necessarily part of the PNP. They could come from somewhere else. That's why we decided that if we can already find a good estimation, a good approximation in 400 milliseconds, when we have this matching here in a period of time which is less than 50 milliseconds, this will say that the theory captures enough so that we can be confident in the electro-diffusion theory. So the way we have explored the parameter C and G, we defined a grid of parameter. We have an initial guess for C and G. And then we have a matrix of possibilities. And we do not have a heuristic like a gradient descent here. We just calculate all of this set of parameters, calculate the solution using PNP, and then we estimate the difference between the voltage we find in the head and the difference in the voltage that we have from the data. We calculate the error, and then we find in the matrix the one such that the error is the minimum one. So again, this is our heuristic. We go from a poor slope to an excellent fitting, so we will retain the set of parameters C and G that will have this property. So how we do it, we explored, we have the space for the G parameter, for the C parameter. And what we did is, for example, we look at what happened when we subtract alpha times a certain quantum delta C and another one delta G. So this allows us to explore in a linear manner the space of parameters. Then we find the pairs C star and G star in the grid for which the error here will be minimum. So it's easy, you just look at the one that has the minimum values. And so if we reach to the point that we are less the C0 and G0 are less than a certain epsilon, we stop the iteration. Otherwise, we just continue the iteration. This is an example here where we just divide by 2, for example, to refine the value of the parameter. So this is the way, once we have a candidate, that if we refined the grid by 2, we can get something which is more close to the optimal parameter. Because again, before we explored the space in a linear manner, and this allows here to refine using not a linear scale, but an exponential way to refine once we have, so this is the exponential exploration of the parameter space. Exploration. Okay? And so then once we have this, we obtain the final couple of parameters. So finally, we have now the input with the optimal value for C and G. We have the parameter of the spine. We go to P and P. We can now estimate the voltage in the neck because we have calculated now I of t. We can use this to calculate, this is the input current from the head to the neck. We can now have the voltage. And if we have the voltage and the current, we can now go and estimate the ratio of the voltage here in the head. So the average means we integrate from 0 to t, 1 over t, and we do v of s ds, where t here is 100 milliseconds. So we go beyond the moment of time where we have the two slopes that are equal, but we decided to go less, not to account for this 400 milliseconds. So we just took this 100 milliseconds, so we integrate, and we said that the effective resistance is in some sense estimated by the average voltage divided by the average current calculated over this period of time. And this is an example of what we found. We have 5 spines, so we estimated the length here. And then we calculated this coefficient C, which has a unit of a capacitance, and here the conductivity. And then using this effective resistance, we estimate here the resistance of the neck. This is the resistance of the neck. And we found here these different values of the order of 100 mega ohms. And so, yeah, this figure has not been translated very well, but basically what you can see here, so we have a region of interest, these two regions of interest that you can see, and this is in this figure, you see the difference between the computed PNP and the voltage V that we obtained from our deconvolution procedure. This was explained in the YouTube one. And we do it here for these several cases. And you see in most of the cases, we have quite a nice fit. Again, indicating that Poisson-Nernst-Planck theory is really the next theory that should be used to, if you are interested in computing and specifically analyzing the voltage in dendritic spines and nanodomains, such as in mitochondria, in the reticulum, endoplasmic reticulum, and so on. And so finally, when we plotted the resistance as a function of the neck length, we found here this approximated linear relationship, which is well known actually in the literature. So to conclude, we used here the intracellular voltage dye. We found that the voltage time transient allow us to estimate an effective resistance from PNP equation, although we think that the resistance is not something that should be used anymore because the transduction from current to voltage is really what is needed. That's why the most interesting output from all what we have discussed today is really to be able to calculate the voltage at any point, because ultimately a channel is sensitive to voltage, not to current, and the voltage depends on the position and the geometrical property of a dendritic spine. That's why we think that the geometry of a spine is an important player of the plasticity. Changing the morphology affects the IV conversion and thus the voltage at any point. And finally, the currents that could be generated inside the dendrite, although we think that the most important thing, again, is the voltage. And possibly this will open the door of using dendritic spine as a coding, as a way to encode information. We think that probably the neuronal code can be in the change of the geometry, not only in the change of the number of receptor in case of synaptic plasticity, but also in the geometry. Most of our code are available on bionumetrics.org, and the method was introduced earlier on in Cartailler Neuron paper 2018. And I hope that with these 3 YouTube videos, what we have done there is much more clear and could be used in the future by the community to analyze voltage in nano domains. Thank you.